Oh, hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright guys, today we're going to start design. Actually restart design. We're going to design a power supply, start the design for a power supply for an audio amplifier. Alright, and I think we're going to shoot for like 500 watts. So this started off as a collaboration with John Audio Tech's channel, his amplifier, and you know, he's moved and he's had some family things. He's had a lot of stuff going on, and I've had a lot of stuff going on this year too. It's been just a crazy year. So trying to get back in the game. All right, so we're going to get back on this design. So let's start with the power factor correction circuit, which we started with before. It's actually going to have 3 stages. We'll do a little EMI filter in front. I'll get to that later. You know, but for right now we're going to do the PFC. Okay, we're going to design the power factor correction circuit. And it's actually active power factor correction. And so we'll have the EMI stage, power factor correction stage, and then the LLC stage is the output stage. Could do an active clamp forward. There's different kind of converters we could do for this, a bridge or whatever. But I think the LLC is very efficient, but mostly because of the way, because it is efficient and the way it gives that efficiency, it's also low noise. And the PFC on the front end, instead of just a big bridge rectifier and big bulk capacitors, it'll also be quieter. It'll be a high frequency switcher versus what I call a low frequency switcher, which is your commutating diodes. Okay, so instead of having a huge peak currents at the top of your waveform, we'll get little currents all the way through the waveform, so that when you smooth that off, it actually looks sinusoidal. So that's how it keeps the power factor correction. All right. So for a nice quiet design, both at the input for EMI and for the output, the PFC stage makes a lot of sense. Now with the PFC stage, it's common that you go high voltage on the output, and that's because you want a universal input. So here in the States, for design for 120, and the people over doing 220, this power supply will work for both of us. So it's called the universal input. So it'll operate. Now the 120, you know, can sag down and do things. Same with, you know, any voltage rail can do that, right? So it actually will go down as low as 85 volts and as high as, I think, 265. Okay, so anything in that range it automatically takes care of. So to do that, and to be a boost converter, which it is, it's a boost converter, it has to always boost. So even when it has 220, the tolerance of the 220, it still has to charge to the peak of that peak waveform above. You want to go a little bit above it, so it's always boosting. Okay, so that's the reason you use the boost converter, and that's why the voltage is usually around 400 volts. This one is like, well, on this eval card we have from Texas Instruments, it's 390 volts. Okay, so I'm going to bring you over to the bench, and we're going to take a look at the bench and see how this thing's hooked up. And what I want to do is really, the boost converter is fairly simple, pretty straightforward to design. The only kind of tricky aspect is the inductor. You have to size the inductor appropriately. And there's a lot of different equations, and I've shown some different equations, and you know, and anyway, it is a little confusing. All right, so we're going to try to simplify that, and I'm going to show you, you know, how we calculate it, and you can see why, if some of those equations actually will melt into this pot that gives us this inductor. Okay, the value we want. So this is your normal boost converter. All right, this is your switching transistor. So when this guy turns on, he pulls this switching node to ground. When he does that, the voltage over here is going to go, you know, the current is going to be pulled through that inductor down here, and you're going to have this circulating current right here during that time this transistor is on, right? And what we do is the current here will actually ramp up until it charges this thing up, and then once we, you know, have it charged up, then we turn it off, and then it discharges, because current won't instantly change an inductor, right? The voltage will, it'll flip, you know, but the current will, once it's flowing, it wants to continue flowing, so it's going to ramp up and it's going to ramp down. And when this guy turns off, the only avenue it has is this diode, and so it charges up this cap. Okay, so dumps into this cap, charges up the cap, and we can boost this voltage up, you know, depending on how much energy we want to transfer from this inductor each time we switch. Okay, so depending on the duty cycle and things like that. All right, so now here comes the PFC converter. The PFC, the input's not DC, it's this pulsating DC. You know, we get a pulsating DC from our low frequency switcher. I know I keep on pushing that because I want to, you know, I think vernacular was kind of lazy, and people just went from linears with everything else was called linear, and everything else that switches was high frequency is called switcher. And it's not really accurate. It's not really, it doesn't give you the right perspective when you're looking and analyzing a circuit. You want to understand that it is actually switching, and it's causing noise, 60 hertz noise. You get these big, huge peak transients at each one of these things. If in a normal power supply, we'd have our, you know, pulsating DC over here, and then we'd have this big old bulk capacitor that would level that out, right? And the voltage here would be pretty much DC with some ripple. And every time when the voltage got high enough above the value of the capacitor, it would forward bias the diode, and you get this huge inrush of current. With a PFC, you don't get that. With the PFC, you get this guy is pulling current all the time, pretty much all the time. So he's pulling current all the way through the waveform, a little bit more, a little bit less, you know, as a sine wave goes up and down. So, and it does a high enough frequency that with a little bit of filtering of the input, the current looks sinusoidal, follows the voltage. So that's power factor correction. So yeah, it aligns the current usage with the voltage sinusoidally. Now, you can have one big peak of current, and it could happen, it could occur at the peak of the waveform, which it doesn't do that. That's why when you don't use power factor correction, you have the power factor is not that great, actually. You know, maybe it's 60%. So you have to have, you know, that extra 40% power on the input to, you know, say maybe you need 140 watts here to provide 100 watts here, because it's not real power, it's apparent power. So with power factor correction, if you want 100 watts here, you provide pretty much 100 watts here, maybe 101 watts. Okay, so much better. And also, you don't get one big surge of current being pulled through all your copper and through your caps and everything. You get lots of little current pulses. So just works way better. Okay, so why is this a little bit more complicated to pick the inductor? Because, like I said, when this switch turned on before, I could say let's say I had 100 volts here and 0 volts here. I could use this equation for voltage. I'd say 100 volts. Now, I manipulate this equation to get the inductor over here, okay? So if I cross multiply, I get the voltage, you know, I get this equation, right? So, and it leaves L all by itself, which I just flipped the equation over and did it this way. So the inductor is equal to that voltage. So if it was a normal boost converter, I'd say 100 volts, and then I'd say, oh, what's my duty cycle? You know, what's my switching frequency, and then how much on time will I have? That's my time on when I'm ramping up, okay? And then the current is how much current I ramp. So let's just say there is one type of boost converter where the current fully ramps up and fully ramps down during every cycle. And then as soon as it drops, it starts again. So there's no DC current. It's all, you know, basically it's turning this sine wave into a whole bunch of triangle waves, okay? And they're right as they hit 0, they turn on again. That's critical current mode conduction. And so what happens is the controller sees that this guy's run out of current, says, hey, switch on again. It's time to fill it back up. Okay, switch off again. So depending on what the load is, it changes the frequency and that to keep things constant here, okay? That's critical conduction mode. That's fine at lower power levels. There's another one where you just set the frequency and you know the inductor is going to run out of current. There's going to be some dead time, and then it's going to do it again. and it's okay, and it's a little bit easier to design. And that one is good for low power, you know, because you're going to charge this up. You know, you have plenty of time to take care of things, your chores. You're going to go off and milk the cow and, you know, feed the chickens or get their eggs. You know, you got lots of stuff to do by the time you have to do another pulse. So there's that one. That's called discontinuous, because you get current and then it's not continuous, it stops. So it's discontinuous. So there's also higher power levels. You want current to be flowing all the time. You want low, higher current. And so you don't want to have to ramp. In the critical conduction mode, the current, if it's triangle, it's essentially, the average current is just essentially half the peak value, right? But at higher current levels, that would mean you'd need, if you want to say 20 amps out here, you'd need peak currents of 40 amps. That might be kind of high. So what you do is go, well, okay, you know what? I'm going to be okay with 20 amps DC, and then the rest of the 20 amps, that part I'll do. Or say 30 amps, and the last 10 amps, I'll ramp up and down. So it's going to take me a while to build that current up. But once I build that current up, then I'm only adding some ripple on top of that. It's a little bit easier to handle at higher powers. And that's the operation mode that we're going to do. Again, if this is 100 volts DC over here and we're calculating that, it's easy, because during the duty cycle pulse, when this guy's on, we know this is 0 essentially, and this is 100 volts. So it's easy to calculate this part of the equation. And we know what we want for these things, so it's fairly easy. Now, with the PFC, we have AC coming in. So, well, pulsating DC, right? We convert to pulsating DC. So when I pull this down, this guy's all over the park. Sometimes it's low, sometimes it's high. So it's not a simple equation. So I can just pick a spot in my head and go, okay, I'm going to pick when it's at peak. And at that point, I want this much ripple. So I can calculate that way, okay? And actually, when I first started doing PFCs, before there's so many app notes and all this stuff out, that's kind of the way I did it, okay? What I'm going to show you is what this looks like, okay, in this converter, on this app. And then we'll see how that works, and we'll see how we calculate this value, and then we can we start getting a better feel, I think, for how to calculate this and how it actually works, and what's the give and take, okay? We want a certain level of DC, and then we want a certain level of ramp time. So if you have, say, 40% ramp time, which you might choose in a normal boost converter, well, and that might help you size the inductor, the capacitors optimally, maybe 30 to 40%. Some people say 20, but a lot of good engineers say 30 to 40% is what I've seen, okay? Now, over here, if you can imagine when the voltage is really low and you're trying to pull a lot of current during that low period, you have this ramp going on, that's going to kind of change things a little bit, right? So if you actually want less of a ripple peak to peak of your little triangle shapes, so that you can operate really well, very close to that 0 line, okay? Let's just come over and take a look at this, see how this guy's working, and see how they did it. That's always a good way to start, is to analyze Texas Instruments circuit. And these guys designed the control chip, so you think they know how to do this part, right? So let's see what they did. Hey guys, a little different backdrop today. On a family vacation, have some friends that own this place, and so yeah, we're lucky enough to come here. But okay, so what we're going to do is, what I was talking about is the waveform on the inductor, okay? I'm going to show you a simulation and see if that helps, but the inductor current ramps up and down, okay? And if it ramps up enough current that it always hits down 0, then that's, critical conduction. If it hits 0, waits, and then comes back up, that is discontinuous. What we want is continuous, because the overall average current, the spikes, the peak currents are a lot less. So the peak to peak currents are a little bit higher, and they just ride the waveform. And as they come close to zero down here, they're kind of small. They kind of stop when they hit the zero for just a moment, you can imagine, because there's no voltage. And then they kind of build up, and then they kind of keep their shape through most of the waveform if they're small enough. If they're large, then as they get closer, they start kind of getting crunched by the voltage not being high enough to allow the peak currents. So we want to get the continuous, and we want to get this waveform. Now this simulation I'm going to show you has, I think it's 50 hertz, might be 60 hertz, but it's slow anyway compared to the on and off times. So in this simulation, the on and off times are actually a lot longer, maybe 8-10 times longer than they really would be. So we'd have a whole bunch more sawtooths in the picture. But doing it this way, you can see the sine wave and the sawtooth at the same time. So that's kind of the idea. So it's just kind of a picture to kind of give you an idea. So let me know if that helps, if you like what you see. And let's just jump in and see that, okay? Okay, guys, this is a little PFC circuit. The only thing we really care about, the circuit on the bottom, just controlling the FET on and off. Other than that, don't really need to worry about this. The frequency and so on isn't, it's kind of set up for this simulation just to make it visible, okay? So now what we're going to look at is, see the orange arrow on top, the current? We're going to see the current coming out of our AC line, okay? And then the green is the voltage, okay? So that's the voltage, and the orange is our current. So let's go ahead and start the simulation. All right, so there you go. Now the green one's the voltage, like I said, okay? And the orange one is the current. So see how the current is following the voltage. Now it is kind of spiky and stuff, but like I said, this is, those orange spikes or triangle waveforms, sawtooth, they are a lot lower frequency than we'd really be running. We'd be running a lot faster, but this just helps the simulation to switch at this lower frequency. So you would have a high frequency, triangle wave riding on top of your sinusoidal voltage, so, but you can see the current is in phase with the voltage now. It's being drawn a little bit less when it crosses over, a little bit the highest during the peaks. So that's that's what it looks like, kind of, okay? Like I said, the frequency is lower than what it should be. Okay, now let's go to this. Let's look at the output now, okay? I'm going to turn off the orange current. We'll keep looking at the input voltage so we can compare. Now, see, here's the inductor. We're going to look at the current through that, okay? Okay, so now there's a current to the inductor. The axis on the right shows the current. The axis on the left shows the voltage. So the voltage is about plus minus 300 volts. And you see the current comes down to about 0, goes back up. So it's the pulsating DC, right? And you see the triangle teeth. Now, if you look close when it's towards the top, it goes from about 50 amps to 100 amps. So it's about a 50 amp sawtooth. And then it drops off in amplitude as it goes towards 0. And then at 0, it just stops switching, and then it picks back up again. Okay, now let's grab that inductor value, and let's make that a little bit lower in value and see what happens. We're dropping down around 200 microhenries. So you see the sawtooth is getting a lot bigger. It's almost coming down to 0 all the time, not quite, so let's go a little bit smaller. Now it's also looking kind of funky looking. It's not quite sawtooth, and that's because of this low frequency switching. Just kind of showing you the amplitude. So you see how the amplitude almost starts at 0 and goes up? So as the value gets smaller, like we get down around 77 microhenries, we'll even go a little bit lower. Go down to 42 microhenries. So you can see how big the sawtooths are, right? And then they're kind of square at the top because, yeah, it's just, if we could switch a lot higher frequency, it would just take a lot longer for the simulation. So it's just kind of giving you an idea. Now we're going to go back up. Okay, I think it kind of restarted. So we went back up to the original 507 microhenries. Okay. Now I'm going to make it a little bit bigger this time. We're going to go up to about, I don't know, 800 microhenries, just over 800. See how the sawtooth's getting smaller? It's actually looking more sawtoothy. All right, so let's go a little bit higher. We'll go to 1.4 millihenries. Now see how small the sawtooth is getting? So it keeps more of its shape as it gets closer to 0. It's because it's a smaller sawtooth, so it can keep on switching as it gets closer. Let's go 2.4 almost. Yeah, we're almost there. Yeah, see how they're nice and small, and they just kind of stop just for a moment down the bottom. So that's kind of the difference between this is, we want to be more continuous like this for higher power, because the average, you know, the peak waveforms, see, we're only going up about 80 amps, just over 80. And those sawtooth things are maybe 10 amps in peak to peak. So, yeah, I thought this EveryCircuit simulation, this is a pretty cool simulation tool. I've shown this before in other videos. I think I have a playlist for this EveryCircuit. And if you guys like it, I'll do more circuits with this so you can kind of see real time how things are going, okay? All right, so I think that gives you an idea. All right, guys, I hope that made sense. The next video we're going to do, I'm going to do another video real quick here where we're actually going to sit at the bench and look at the waveforms, okay? So I'll show you the real life waveforms. And yeah, maybe this will make sense. And from those waveforms, we can calculate the inductance that is actually in the circuit on this Texas Instruments eval card, and it'll just kind of help us learn how to come up with the inductor and what it means to have a bigger or smaller inductor by watching these waveforms. All right, hey, thanks for watching. Big thumbs up to all you guys. Happy Thanksgiving. It's kind of late Thanksgiving now. It's kind of day after, but anyway, happy holidays, and big thumbs up to my members, and big thumbs up to my patrons. You can become a patron, all that stuff down below. We're going to get cranking on this design. It's going to be kind of fun and pretty cool background, huh? All right, we'll see you guys.